Like a child that never stops asking why, no matter what you answer, so have I been driven by the question why all my life. It has pushed me to dig deeper, to go to the next level and the next level. And so I've ended up studying the smallest things we know to exist. I invite you to join me on a journey, exploring, mining to find nature at its smallest, most fundamental. You will see that this smallest scale is deeply linked with the largest scale, the universe as a whole. And you will get to see that this influences how we perceive our place in the universe. And so we begin by taking something, anything, and cutting it into smaller and smaller pieces. Eventually, you will come to a piece which cannot be further divided, no matter how good the tool for cutting. You may think that this is the atom of the elements, but no, the atom is a composite mess. We need to dig deeper. But if you catch an electron, which we know and love from electricity, swirling around the nucleus of the atom, and you dig into the nucleus itself, into the protons and neutrons, to find a quark inside of them, you will have found what we, as of today, believe are fundamental building blocks of nature, elementary particles. And these are small. They have shown no substructure down to the size of 10 to the minus 18 meters. That is, take a meter, cut it into 1 billion pieces, take one of those pieces, and cut it 1 billion times more. Small. But in fact, we believe that fundamental building blocks of nature have no size at all. If you find that hard to imagine, don't worry, you're in good company. That goes for many aspects of the world at its smallest scale, where quantum physics is the name of the game. Our human intuition has been built up by our sensory experience in this macro world, and it simply won't do at the quantum world. Which is not to say that we don't know what's going on there. We can calculate and we get sensible answers. It's just that these answers are very hard to reconcile with how we perceive the world to work. Let's get back to the quark and the electron. These are matter particles, that which builds all the things we see around us, ourselves included. But they are not the full story. In the early 1930s, a whole new component of matter was found, which in some sense behaved completely opposite of ordinary matter. Hence, it was given the name antimatter. Don't be fooled by the name. Antimatter is perfectly good matter. Now, more than 80 years later, antimatter in and of itself is old news. We even use it actively today within the field of medical physics for preclinical imaging in something called PET scanners. The P comes from positron, which is the antimatter version of the electron. But there is something special, and that is the relationship between matter and antimatter. Perhaps they are the very best of friends. Perhaps they are fierce enemies. At any rate, whenever they meet, they disappear. They get obliterated, they annihilate, and are turned into pure energy in the form of light. So here is where it gets interesting. Yes, downright existential. If we go back in time, to moments after the Big Bang, in this early, hot and dense state of the universe, which was the infancy of our universe, matter and antimatter existed in equal amounts. Eventually, all of that matter and all of that antimatter would meet. But if that were the case, there would be only pure energy left in our universe, no matter, nothing out of which you could build anything. But we are here. And we're asking ourselves this question: how come we are here? What caused this slight imbalance between matter and antimatter to which we can thank our existence? We don't know. There are many things that we don't know about antimatter, and getting to know it is a challenge because antimatter does not linger around. On the border between Switzerland and France resides the world's one and only antimatter factory at the European laboratory CERN. That's where I work. The people who work there are trying to get to know antimatter better. And, as you may now appreciate, trying to understand antimatter better is like trying to understand our place in the universe better. We can do so thanks to the help of a machine called the Antiproton Decelerator, whose job it is to make antiprotons move slower and slower until sluggish enough for us to capture and study. The amounts that we get are tiny. With the current pace, it would take us 10 times the lifetime of the universe to get 1 gram. But we do get something, and we are able to study it. Currently, there are 5 experiments connected to the Antiproton Decelerator: Aegis, Alpha, Asakusa, ATRAP, and BASE, all of which are trying to look at antimatter from slightly different angles to collectively get to know as much as possible. I and my colleagues in the Aegis experiment want to see how antimatter responds to gravity. Essentially, we're trying to reproduce the famous experiment by Galileo Galilei in the 14th century, when he dropped heavy and light objects from the Leaning Tower of Pisa to find that they fell with exactly the same speed. The difference? We want to release antihydrogen, the lightest antimatter element. Now, antihydrogen is nowhere around, so we have to produce it ourselves. One of many challenges that we're faced with. But let us focus on the basic idea, the basic question that we're asking ourselves. Imagine that you held an apple made of antimatter in your hand, an anti-apple, and you let it drop. How would it fall? Just like an apple made of ordinary matter would? Or would it fall slightly slower, perhaps much faster? Or, and this is the real oddball here, would it fall upwards? It's not expected that it falls upwards, but no one really knows because no one has performed the experiment. So let us entertain the idea for a while that antimatter behaves so unexpectedly as to fall upwards. We believe that there are no large structures made of antimatter out there in the universe, and I'll explain why. For this, you need to recall that whenever matter and antimatter meet, they get turned into pure light. So, if there were a region of antimatter out there, it would have to border to a region of matter. After all, we are made of matter. And from this horizon, light would stream. So, we look up into the night sky, we peer deep into the universe, and we see no such light. But if antimatter falls upwards when released here at Earth, it means that matter and antimatter gravitationally repel each other, which means that the regions wouldn't meet, and there would be no such light for us to see. In which case, for all that we know, there could be an anti-world somewhere out there. Now, let us for a moment go back to quantum physics. When you dig to find nature at its most fundamental, you will eventually, inevitably, encounter symmetries. Symmetries are deeply woven into particle physics. Indeed, it's the heart of the theory. Symmetries decide what may or may not happen and which forces are at play. With a symmetry, we mean that something looked the same before and after a change, that it is invariant to the transformation. Like a uniform ball, if you twist it around, it looks the same no matter what. It is symmetric. Likewise, if we performed a physics experiment here today, we would get the same result as if we would have performed that experiment tomorrow on the other side of the globe. which means that the physics involved has to be invariant, symmetric, with respect to changes in time and position. We expect nature in its simplest and most fundamental form to be symmetric. And it is, for the most part. So we expect nature to be symmetric in her gravitational treatment of matter and antimatter, that they fall in the same way. So it is not at all expected that antimatter falls upwards, but it is not impossible either. Albeit not plausible, it is theoretically viable. We simply don't know before we go out and have a look for ourselves. And we have been surprised before. I can tell you that when the cosmic microwave background radiation was discovered, initially, pigeons were blamed for obstructing the measurements by littering on the experimenter's antenna. Or I could tell you that when the muon particle was discovered, a surprised and perhaps slightly dismayed theoretical particle physicist blurted out, "Who ordered that?" Oh yes, nature certainly has the capacity to surprise us, even shock us, as it did when we first had a look at a particular symmetry called charge parity. Charge parity flips the electrical charge and all of the spatial coordinates. Left becomes right, forward becomes backwards, up becomes down. And now you will get to know what the real difference between matter and antimatter is. It's the flip of the electrical charge. Whereas an electron has negative electrical charge, the positron has positive electrical charge. So charge parity transforms a matter world into an antimatter mirror world. And we expected the rules for these constellations to be the same, that the situation was symmetric. So when it was found, utterly unexpected, that nature violates charge parity, physicists felt like the ground had been removed from underneath their feet. That charge parity is violated means that the processes involving matter and antimatter move at slightly different speeds, which could be the explanation for why matter won over antimatter in the early universe. But in our standard model of particle physics, the processes that violate charge parity are simply not strong enough to explain the apparent asymmetry between matter and antimatter which we observe in our universe today. So we have to look further. So we know now that antimatter behaves unexpectedly. The question is how much and in which ways? And that's what we're trying to find out. We will soon learn more about antimatter from the ongoing experiments. We are even upgrading. Soon, a new machine called Elena will go online, improving upon the job that the Antiproton Decelerator does. It will provide more antimatter for us to study. Most likely, we will find that matter and antimatter fall in exactly the same way, in which case we will have to look further for solving the mystery of the missing antimatter, why there is something instead of nothing. We know that there are several missing pieces to our understanding of nature, and we are continuously searching, probing with a range of multifarious experiments to get to know the universe and our place in it better. Ultimately, that's what we humans do. We search for understanding, we seek to learn, we explore. It's a fundamental part of our humanity. So, I would like to end on a personal note with an encouragement to you. Nurture your curiosity. I believe it's the best thing we can do for the world. Being open and skeptical will bring you the humbling experience of getting surprised and having to revise your view upon the world. I'm rather sure that when you look at me, the first thing that meets the eye is not a scientist. But that's just the thing. We're all scientists at heart, no matter what we dress like, what we look like, who we are. And we were all active scientists at one point in our life, exploring, performing experiments to get to know our surroundings better when we were kids. So find back to your inner child. Never stop asking questions. Cultivate your curiosity. You never know when you might stumble upon something unexpected.